device. Yeah, the part before the meter is mainly about physics in order to introduce the specific expression of the optical gain. But now we will take the optical gain as some kind of background knowledge and model the whole expression with an easier expression. The expression in a more easier form. All right. So in laser device, we need to consider the dynamic between the carriers and photons. So the rate equation of carrier and photons are important. They need to be considered simultaneously. And then we will introduce an important concept of the threshold condition. What does threshold mean? Is it the same with the so-called transparent condition? They are related, but the threshold condition isn't the transparent condition, and we will show you why. And now we will tell you, like in normal people who doesn't take a very deep semiconductor physics, how will they describe gain with the carrier density? All right. So this is the very simple structure of the semiconductor laser diode, and you might see that in the midterm. And the structure is pretty similar like this. First, the epi structure contains three parts: the N parts, the P parts, and the active parts. And the active region might be simultaneously as the waveguide, or the active region could be different structure with the waveguide. If the active region is equal to the waveguide layer, then we call it the double heterostructure layer. However, because the wavelengths of the photon and the carrier are quite different, so we might add another few confinement factor, confinement structure, or so-called quantum well, to confine the carriers. Then in this case, this is the separate confinement heterostructure, or we call it SCH lasers. Okay, and the parts outside the guiding layer is called cladding. This is the same from the optical fiber. So we have a guiding layer and the P side cladding and the N side cladding. And when carrier are injected from the both P side and N side, they will recombine in the active region and generate light. Okay, but there's always some defects or some imperfection about the injection. Not all the carriers injected will be contributing the light emission. For example, if an electron is injected into the active region, however, because the temperature is finite, so we have something like a distribution like this for the bulk case. And the other side, the P side, the energy difference or energy barrier probably is not very high if you didn't take the design seriously. Then the whole tail might overflow the structure. Then the carrier will be consumed by leaving the active region. So this is called the carrier overflow. There's another way to leave the carrier is called hot carrier. Because the carrier is injected, before the carrier is emitting in the active region, you need to be captured by the quantum wave first. For example, I set a trap in the middle, and I walk down. I need to put my leg in, and I get trapped. But however, if your carrier runs really fast, and it doesn't have much time to interact with the photons, so the carrier is still at high energy, it might directly surpass the active region without really going to the active region. Then this is called the hot carrier effect. When does this happen? It usually happens when your quantum wave is too thick. So your injected carrier don't have much time to stay in the active region. So it don't have a chance to be interacting with the photon, then be captured inside the active region. So this is another carrier leakage mechanism called hot carrier effect. So these two are different. Carrier overflow, the carrier has to be captured by the quantum well first. But according to thermalization, some part of them might be further leaving the quantum well. Well, they are further leaving the quantum well due to the finite energy barrier. But if your confinement structure is too weak, and the carrier don't have much time to stay within there, it could be also leaving the active region. So there's another way to leave the carrier region is that you might have some local defect. For example, you might have a leaky path with metal inside, or you have a screw dislocation. The carrier might choose to leaving or just pass the active region without really getting to the active regions. So to sum up, we can use one number to evaluate the effectiveness of the carrier capture. We call it the injection efficiency. Injection efficiency, that means the number of carrier really vanished in the active region. No matter it vanished by radiative way or non-radiative way, as long as it vanished in the active region, divided by the carrier really injected from the electrode. Yeah, because some might just passing it, or some might be leaking from the other path. So this defines the injection efficiency. Now we just explain why this injection efficiency might not be 1. It has so many 1, 2, 3, or even more mechanisms to explain why carrier is not captured by the active region. Okay, so now we can consider the carrier density in the carrier density in the quantum well. So this is wrong. In the active region should be like this. Let's call the capital N as the carrier density in your active region. Then dN over dt is equal to G minus R. What does G mean? G means generation. Generation means you have some way to increase the carrier density of your active region. It might be optically pumped, because the one photon is absorbed by your quantum well. Then it generates one carrier and one electron and one hole. So it's called generation. And its number will be the photon energy absorbed, delta P, divided by h mu, because this is the energy of one photon. Then divided by VA. VA is the active volume of the volume of the active region. So total energy per photon. So this is the total energy absorbed. The total number of photons absorbed is equal to the total carrier generated divided by VA. Okay, so this is the generation by optical pumping. However, if you generate a carrier by electrical pumping, that means you put the power on and the injected current. So the electrical pumping, the generation should be total current divided by Q. So because this is the charge of one electron, so I divided by Q is the number of the electron or hole injected from the electrode. But only zeta I, the sum of them really enters the active region. So you need 2 times zeta I. Then again divided by its volume. So that will be the generation of the electrical pumping. Then the recombination term, it need to consider all radial recombinations, including spontaneous emission, stimulated emission, and the non-radiated emission. Non-radiated emission further conclude SRH and the surface recombination, OJ, blah 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 blah. So it's because all the non-recombination that you can put it together because they have the same property. So if it's in only 3 classes, it's important. One is spontaneous emission, stimulated emission, and non-radiative emission. So we can write down the total recombination with different form. Just depends on which one is more convenient for you. If we take the ABC model, that means we need to decouple the Shockley Hall by spontaneous emission and the OJ into Photon. Yeah, then we can write down like the second line. But for the laser diode, because we usually don't differentiate that much, we do it a more simple expression. We call it tau divided by n divided by tau. Tau is the carrier left time. So obviously, in this case, the carrier left time is a function of carrier density as well. So that will make this expression to be correct in any form. It's n over tau, but tau is the function of carrier density. So as long as this can change, it can be written down as this way in any purpose. So to simplify the rate equation, we can also simply write down like this: n divided by carrier lifetime. That means the frequency of the carrier will recombine with something else. Yeah. So 1 divided by time will be the probability or the occurrence frequency. Okay. Okay. So finally we put the RST, but we haven't showed it. We haven't expanded RST yet. So the net rate of the carrier density in the quantum world should be dN over dt is equal to generation minus both non-radiative and radiative recombination besides stimulated emission, because this is an important term. This one includes scan, this one don't. So we need to separate these two terms. So this is the generation minus recombination. And then we put the stimulated emission outside and dump everything else together with only one term. This is only to make the expression more cleaner, or it will be pretty difficult to read. Alright. So there's also another way to simplify the AN plus BN plus minus 3 by defining the radiative efficiency. The radiative efficiency is the rate of spontaneous emission divided by O10. So this is the radiative emission. Okay, so we can also doing this whole term AN plus BN squared plus CN squared, the whole term by BN squared over zeta. We can simplify the whole term plus BN squared plus CN cubic as the zeta R, radiative efficiency, times BN squared. We will also use this equation later. So we want to know what happens if we keep exciting the material continuously to reach a steady state. Steady state means that all the term is not a function of time. It don't change with time. So the dN over dt has to be 0. So that means this whole term should be equal to 0. Then that means the generation should be equal to the total recombination. So while the device is far away from lasing, the optical gain is small, minimal, or even negative. So we can simply just neglect the IST while the device is under low pumping. So we can write down like this. Then the total output power from the active region could be something like this. Bn squared times Va times h mu. Because Bn squared is the total number of photons generated per volume, times its volume, then this is the total number of photons generated. Then number times the energy per photon, so that will be the light power generated from your active volume. Okay, so after some rearrangement, we have this. P over h mu, the number carrier photon generated. I divided by Q, the number of electron injected, times zeta I, because some part will be missing, not going into the active region. Okay, and the loss part times zeta R, because some parts of the carrier will be will be consumed by non-radiative ray. Okay. Then the efficiency in the LED region, that means the optical gain has a role, yet the efficiency could be writing down like this. Then we can define the three different kinds of efficiency. This is also often used in evaluating the efficiency of LED. The first is called the internal quantum efficiency, IQE. IQE is the photon generated divided by the carrier injected. That's how many electron pair will be transformed into the photons. But that only happens within the small device. So that will be P divided by h mu. That we subscript active, that means we only count the part in the active region, not the part outside the device. Because some photon emitted might not be observed by you. So we need to decouple these two steps. So P active region divided by h mu divided by I over Q. So that will be zeta R times zeta I. Okay, so now the photon is generated in the quantum well or the active region. It might not be observed by you because it might be reabsorbed in the device while your device is well polished square. Then you have some waveguide effect inside, so it not necessarily be observed. So we can divide the second term called the light attraction efficiency. Light attraction efficiency means the photon generated in the active region, and the photon really emitted and observed by you. Yeah, because you need to leaving the device to be useful. Okay, so this is the light attraction. Surely there will be some the number less than 1 because the photon don't generate it from nowhere. It must be generated first, then be emitted by this device. Then we can tie this together called external quantum efficiency. Yeah, because this is efficiency defined by the user, not by the device. So that will be the photon really emitted from the device divided by the carrier injected from the outside. So you can divide it by this term and the times this term again. Okay, yeah, because these two will cancel each other. So that will be IQE times LEE. Okay, so putting them all together to the PLED could be writing down like this. It should be h mu divided by Q times I times EQE. Okay, so it will be something I divided by Q is the number of carrier times the efficiency, the number of photons you observe, times the energy per photon. Okay, so this is pretty straightforward, and it will be expressed like this. Okay, but for laser, the optical gate we need to be considered, and this happens when the carrier density is high. As you calculated in your homework 3, I assume you really try to calculate that. Yeah, I believe you did, or you in the midterm will be very difficult for all of you. Anyway, so now we also need to count the photon energy of your device. What does the photon energy mean? That means the optical energy divided by h mu. Then we can simulate it as a number of photons. So we can also consider something called photon energy. So we write NP means the number of photons, because we in order to not to confuse with the number of carrier. So number of photons is N with subscription P, dN over dP. Then similarly, it should be the generation minus consumption. The generation is the RST still plus the spontaneous emission, because this generate photon, stimulated also generate photon. But stimulated emission for a specific mode, we discussed that because we need a cavity mode first, then we have a spontaneous emission. So since you have so many cavity mode, if we only care the emission rate of one mode or one photon, so it need to times beta SP. Beta SP, what's the definition of beta SP? Beta SP is the total spontaneous emission rate. Because you need to have a mode first, then you have spontaneous emission. But now this cavity is large, you might have 1 million available mode in your device. But we only care one of them as your interested mode. So in this case, your beta SP will be 1 divided by 1 million. Then it will be a pretty low value. Yeah. The reason is because your cavity is so large, so you have some optical mode. However, if you have a quite small mode or very small cavity, and there's only very few available optical mode, then this beta could be close to 1. Yeah, that's another case. But for the edge emitting laser or VSO, whose cavity is much larger than the photonic wavelengths, then this number is usually quite low. Probably 10 minus 4 older or 10 minus 5. That depends. Okay, anyway. So the total spontaneous emission rate need to times the beta SP for counting the photons with a specific mode, times the RST, because RST only allows when there's a mode exists, and then times the confinement factor. Because in your cavity, not every part of your device is emitting light. So we need to times confinement factor to normalize the part really have effect with the light matter interaction. Okay, so that's you also calculate that in your midterm. Okay, so this is the number of photons generated in the AT region. Then similarly, it will be consumed by some way. For example, free carrier absorption, and probably some like double or like a free carrier absorption, or just light scattering due to effect anyway. So we can also simply write down with a simple term, NP divided by tau p. Tau p will be the photon lifetime in your carrier. Smaller the tau p, that means the your optical energy will be dissipated pretty soon by some means. Scattering, free carrier absorption, anyway. So this is only a numerical expression, minus NP divided by tau p. Okay. And for implant lasers, we calculated in the lecture 5, I suppose. We calculated the gamma XY in the effective mass way. But in a Fabry-Pro laser, we have some parts of the laser not emitting light. We will show you a case. Anyway, so the total confinement factor need to consider the implant mode profile, the confinement factor from the implant mode profile, and the actual confinement factor, which means the real length of the active region divided by the length of all cavity. Let's consider a structure like this. This is the quantum well. And the laser is long. For some reason, there's no quantum well from here. So this is called the active region. And the other part with no quantum well, which is not emitting light, called the passive region. You might be interested why we have a passive region. Yeah, that's a very good question. We will take probably 2 weeks to explain why a passive region might be useful. Okay, so in this case, the total cavity might be L. And those parts with active region, which really emits light, could be LA. And those without active region, we can denote it as LP. Then the actual confinement factor could be simply write down as LA plus LP times LA with a enhancement factor. Okay, so new concept keeps coming out. What does the enhancement factor mean? Enhancement factor means while if your activity is so small, it is important to see whether it stays in the node or the maximum of the electric field. If the interaction is at its maximum, then your confinement factor will be enhanced. But if your activity is at its node, for example, if you have a cavity like this, and this is your optical mode. Okay, so probably this is the E squared. Then, if your active region is not in this direction, if your active region is something like this, okay, and this is active. If your active region lies down with the highest optical energy, then your confinement factor will be enhanced. So this will have a high gamma enhanced. However, if you put your quantum well here, unfortunately you do the really bad design, then you have a low NH. Okay, we will also tell you how to re-evaluate the actual number of the enhancement factor probably in the lecture 13. Okay, so it will be meet that again and again and again. Okay, anyway, so now we need to plug in the real expression of your stimulated emission to fulfill the Ray equation for both carrier and photons. So let's start again. If from lecture 6 we have optical expression, gain expression like this, and after some rearrangement, we have the gain should be 1 over NP times dNP over dd. Then the dd can be further written down as the group velocity times the interaction time. So, and the dNP over dt could be expressed as your stimulated emission rate. Okay, so RST is Vg times NP times G. Then we can plug it to get the coupled Ray equation for laser diode. The first one is the carrier, dN over dt, should be the carrier injection minus recombination beside stimulated emission, because this term is irrelevant to G. Minus Vg NP G, this is a stimulated emission, which is relevant to G. Okay, so this is the Ray equation of the electron. Then we can also write it down, the dNP over dt. This is the Ray equation of the photon. This is beta ISP times ISP. Yeah, because we only consider a specific mode. Times, this is RST. So, light matter induction will be a positive term for the photon because it generated photon, but a negative term for carrier because it will consume carrier. Yeah, but that also depends on the sign of G. If G is positive, then it is a negative term. But if it is negative, then it will positive term. So the term of here, so it's important if it is absorbing or emitting. Okay. Then the generation term, this whole term is the generation of photon minus the consumption of photon by some other ways. Okay, so we need to solve these two equations simultaneously to describe the behavior of our laser diode.